Right now, in your car, in your fridge, in the hospital down the street, in the elevator you took this morning, in the aircraft flying overhead, there are more chips made in China than most people would believe possible. Not in your phone, not in your laptop. The famous chips are not Chinese, but everything else? Everything that keeps the modern world physically running, the chips inside the airbag, the ventilator, the transformer, the traffic light, the water pump, the missile guidance system. A growing share of them come from one country, and almost nobody noticed it happening. Not a single one of those runs on a cutting-edge chip. Not one uses anything designed in the last 10 years. They all run on semiconductor technology that the advanced chip industry considers obsolete 28 nanometers and older. Some of these designs have not fundamentally changed since the late 1990s. And while the entire world spent the last 5 years arguing about who would build the most advanced 2-nanometer processor, one country quietly built enough factory capacity to produce roughly a third of the entire global supply of these chips. The ones no one writes headlines about. The ones the world literally cannot function without. That country is China. The factories are not planned. They are already built. Several are already running. And by the time most Western governments noticed what was happening, the math had already changed. Here is the part that makes this genuinely alarming. Almost every dollar of Western semiconductor investment, the CHIPS Act, the European CHIPS Act, the tens of billions in subsidies, was aimed at the top of the chip pyramid, the glamorous race, the frontier. Almost nothing was allocated to protect the base, the part everything else sits on, and China is now building that base for the entire world. There are roughly 2 worlds inside the semiconductor industry, and only one of them gets any attention. The first is the cutting-edge world 2-nanometer and 3-nanometer chips manufactured by TSMC and Samsung using the most complex machines ever built. These are the chips that power flagship phones, data center GPUs, and the AI models everyone is arguing about. They cost billions to develop, require equipment that only one company in the Netherlands can build, and represent the absolute peak of human manufacturing precision. That is the world Nvidia lives in. That is the world the export bans target. That is the world the headlines are about. The second world is everything else. Microcontrollers that cost 40 cents and manage the motor in a washing machine. Power management chips that regulate voltage in a laptop charger. Sensor interfaces in automotive safety systems. Timer circuits in industrial equipment. Analog to digital converters in medical monitoring devices. Communication chips in agricultural sensors and smart grid infrastructure. These chips are manufactured at 28 nanometers, 45 nanometers, 65 nanometers, 90 nanometers. Process nodes so old that leading-edge foundries stopped investing in them years ago. The designs are mature, the margins are thin, the technology is unglamorous. But here is the detail that makes these chips harder to replace than most people realize. Every chip embedded in a safety-critical system, a car, a medical device, an aircraft, a weapons platform, has to go through an extensive qualification process. Testing, certification, regulatory approval. That process can take 1 to 3 years, and it is locked to a specific chip from a specific manufacturer at a specific fab. You cannot simply swap in an equivalent chip from a different source and call it done. The qualification starts over. That means once a product designer sources a mature node chip from a Chinese foundry, and the chip passes qualification and enters production, switching away from that supplier stops being a procurement decision. It becomes a redesign project. Months of re-engineering, years of recertification. In the automotive industry, the cost of requalifying a single chip across a vehicle platform can run into the millions. This is why the dependency, once established, is so sticky. And it is why China's strategy of offering the lowest price to win the initial design win is so effective. The lock-in happens before anyone realizes it is a lock-in. And these chips make up the overwhelming majority of all semiconductors used on Earth. Not by revenue, by volume, by the sheer number of chips embedded in the systems that keep civilization running. The cutting-edge chips get the press conferences. The mature node chips keep the lights on. And that distinction is exactly what makes what China is doing so consequential and so hard to counter. Starting around 2020 and accelerating sharply after the US imposed its most aggressive semiconductor export restrictions in 2022, China began a fab construction campaign, unlike anything the semiconductor industry had ever seen at this process tier. Not fabs for cutting-edge chips. China was largely locked out of that race by equipment bans. Without ASML's extreme ultraviolet lithography machines, manufacturing below roughly 7 nanometers is effectively impossible. Western policymakers treated that as mission accomplished. China could not build the most advanced chips, threat contained. But here is what the export controls did not cover. The equipment needed to manufacture chips at 28 nanometers and above older lithography systems, etching tools, deposition machines, is widely available. Much of it is produced by multiple suppliers in multiple countries. Some of it China already manufactures domestically, and none of it was restricted because nobody considered mature node chips a strategic concern. China used that gap aggressively. Between 2022 and 2026, China brought online more new semiconductor fabrication capacity at mature nodes than any other country. The numbers are difficult to overstate. SMIC, China's largest foundry, expanded rapidly across multiple facilities, including a major new fab in Shanghai and expansions in Shenzhen and Tianjin. But SMIC was only part of the story. Hua Hong Semiconductor, another major Chinese foundry, expanded capacity specifically targeting automotive and industrial chips. Dozens of other firms, many backed by provincial governments, competing to build semiconductor hubs, launched fabs across the country. The funding mechanism was as important as the scale. In China's semiconductor strategy, the central government sets the direction through programs like the National Integrated Circuit Industry Investment Fund, commonly known as the Big Fund, which has deployed tens of billions of dollars across 2 phases. But provincial and municipal governments pile on with their own subsidies: free land, discounted utilities, tax holidays, and direct capital injections. A fab project in China can receive layers of support from multiple levels of government simultaneously, creating a cost structure no market-driven Western investment can replicate. The result is a construction tempo that looks irrational by private sector standards, because it is not operating under private sector logic. It is operating under industrial policy logic, where the goal is not return on capital, but market position. By several industry estimates, China is on track to control roughly a third of all global mature node chip manufacturing capacity by the late 2020s, more than double its share from just a few years earlier. One country, doubling its share of the world's most widely used chip category in half a decade, while everyone was looking somewhere else. The reason this happened in a strategic blind spot is not complicated. It is a bias built into how the semiconductor industry talks about itself. In semiconductors, progress is measured in one direction smaller. 2 nanometers is better than 3. 3 is better than 5. The industry's entire culture, its media coverage, its investor attention, and its government engagement are organized around the leading edge. That is where the breakthroughs happen. That is where the Nobel Prizes are. That is where Nvidia and TSMC became trillion-dollar companies. Mature node chips are, by definition, the opposite of progress. They are old technology, they are boring, they are commodity products with thin margins. No politician holds a ribbon-cutting ceremony for a factory that makes 40-cent microcontrollers, and that perception shaped everything, including policy. When the United States passed the CHIPS and Science Act in 2022, The vast majority of the $52 billion in manufacturing incentives was aimed at cutting-edge and advanced fabs. TSMC received billions to build in Arizona, Samsung in Texas. Intel was expanding in Ohio and was awarded the single largest grant, nearly $8 billion, for leading-edge facilities. The messaging was clear: the US would lead in the most advanced chips on Earth. A small fraction was earmarked for mature node and current generation capacity, but relative to the scale of the problem, and relative to what China was simultaneously investing, it was not close to enough to change the trajectory. The European Chips Act followed a similar logic. So did Japan's and South Korea's semiconductor strategies. In every case, the political energy and the funding followed the frontier. Almost none of that money was designed to secure the supply of the mature node chips that actually run most of the world's infrastructure. The military equipment, the medical devices, the automotive systems, the energy grid, the industrial base, all of it dependent on chips manufactured at nodes that Western subsidy programs largely ignored. The strategic assumption was that mature node chips were a commodity, and commodities take care of themselves through market forces. China bet that the assumption was wrong, and the bet is paying off. If this story sounds familiar, it should. It is the same industrial pattern China has executed in solar panels, EV batteries, steel, and shipbuilding. And the sequence is almost identical. Step 1. Identify a sector the West treats as low margin, unglamorous, or strategically unimportant. Step 2. Invest at a scale no private sector competitor operating under market return logic can match. Step 3. Build enough capacity to become the dominant global supplier. Step 4. Use cost advantage to undercut every remaining competitor until the market consolidates around Chinese production. In solar panels, China captured over 80% of global manufacturing capacity using this approach. In EV batteries, over 75%. In each case, Western industries recognized the dependency only after it was structurally locked in, and in each case, the response came too late to prevent the consolidation, only in time to manage its consequences. The early signs in mature semiconductors are already visible. GlobalFoundries, the only major American headquartered foundry with significant mature node capacity, has publicly discussed the challenge of competing against subsidized Chinese production. European foundries face the same pressure. Even UMC and Vanguard in Taiwan, which built their businesses on mature node manufacturing, are watching Chinese competitors erode their market position with pricing that reflects government backing rather than production economics. When a competitor can sell at or below cost indefinitely because losses are absorbed by the state, market-based competition does not work. The outcome is not determined by who makes the better chip. It is determined by who can sustain the lower price for longer. And that is a contest the Chinese model is structurally designed to win. Mature node semiconductors are following the same curve, and the mechanism is already visible. Chinese manufactured mature chips are already entering the global market at price points significantly below what established foundries in Taiwan, South Korea, and the United States can match. Some industry analysts have reported pricing 15 to 30% below prevailing market rates for equivalent chips, a gap that reflects not just lower labor costs, but the accumulated effect of subsidies at every level of the production chain. For a product buyer, an automotive company sourcing a $2 microcontroller, a medical device manufacturer buying a power management chip, an industrial equipment maker choosing a sensor interface. The math is the same math that drove every other industry toward Chinese supply. Same spec, lower price, reliable delivery. Procurement departments do not make geopolitical decisions. They make cost decisions. And the established foundries, the Taiwanese, Korean, Japanese, and European firms that currently produce many of these chips face an impossible choice. Match the price and destroy their margins, hold the price and lose the customer. Either way, investment in new mature node capacity becomes harder to justify, which makes the dependency deeper, which makes the Chinese cost advantage more structural still. It is a consolidation loop. And just like solar panels and batteries, once the global supply base consolidates around the cheapest producer, reversing that consolidation becomes almost impossibly expensive. The question is no longer whether this is happening. It is whether it has already passed the point where it can be stopped. Here is where this becomes a national security conversation, not just a trade one. The mature node chips China is mass producing are not just in washing machines and thermostats. They are in weapons systems. Specifically, they are in the guidance systems of missiles, the control electronics of drones, the sensor packages in military vehicles, the communication hardware in encrypted radios, and the power management circuits in satellite systems. Modern military equipment does not run on the latest Nvidia GPU. It runs on hardened, radiation-tolerant, extensively tested chips manufactured at older process nodes, precisely the chips China is now producing at scale. These chips are chosen for military use because they are proven, reliable, and stable. Switching to a newer process node is not an upgrade. It is a multi-year, multi-billion-dollar requalification effort that most defense programs cannot absorb. During the global chip shortage of 2021 and 2022, this vulnerability was exposed in the civilian world, and the speed at which it happened stunned the entire automotive industry. Auto manufacturers shut down production lines not because they lacked advanced processors, but because they could not source enough 40-cent microcontrollers built on decades-old technology. General Motors at one point had tens of thousands of nearly complete trucks sitting in parking lots, waiting for a single chip to be installed before they could ship. Ford reportedly lost billions in revenue. Toyota, the company famous for perfecting just-in-time supply chain management, could not get the chips it needed. The shortage was not caused by a lack of global capacity in any absolute sense. It was caused by an allocation problem when pandemic-driven demand surged for consumer electronics. Foundries shifted capacity toward higher-margin products, and the automakers who needed cheap, simple chips were told to wait. The lesson was clear and brutal. The chips nobody valued were the ones nobody could live without. That shortage was caused by pandemic disruption and demand spikes. It was temporary and unintentional. Now imagine the same disruption but deliberate, not a pandemic, an export restriction, a licensing requirement, a diplomatic condition. China has used these tools before in other commodity sectors: rare earth minerals, gallium, germanium. The mechanism is well established and legal under Chinese law. If a significant share of the world's mature node chip supply flows through Chinese fabs, the leverage that creates is not theoretical. It is the same leverage any dominant supplier holds over any critical commodity. And the customers on the other end, the defense contractors, the automakers, the medical device companies, the grid operators would face the same choice every other industry has faced when a single source dependency becomes apparent: pay more, wait longer, or accept the terms. The obvious response, build more mature node fabs in the West, sounds simple and is anything but. The economics are the core problem. A cutting-edge fab is extraordinarily expensive to build, but the chips it produces sell for high margins, tens or hundreds of dollars per chip. Investors will fund that. A mature node fab is cheaper to build, but the chips it produces sell for cents. The return on investment is marginal at best, and in a market where Chinese competitors are willing to sell below cost to gain share, it may be negative. No private semiconductor company in the US or Europe is going to build a new fab to manufacture 40-cent chips at a loss. That is not how capital allocation works in a publicly traded company. The only way it happens is through government subsidy, and as of now, the subsidy programs are not structured for it. There is also a concentration risk that most people have not fully absorbed. Much of the world's current non-Chinese mature node production is located in Taiwan. TSMC and other Taiwanese foundries produce a significant share of the legacy chips that the West depends on. If the strategic concern about semiconductors is supply security, and that is what every government says it is, then relying on Taiwan for the base layer of the chip supply is not a solution. It is the same single point of failure problem, just in a different country, and one that sits 100 miles from the Chinese mainland. There is a workforce problem too. The engineers and technicians who operate mature node fabs are a different talent pool than the ones building cutting-edge facilities. The equipment is different, the process chemistry is different, and the career incentive for a young semiconductor engineer to specialize in technology from the 1990s rather than the technology of 2026 is, frankly, low. The glamour gap that made policymakers ignore mature chips also makes it difficult to attract the people needed to build them. And there is a time problem. Even if policy changed tomorrow and money flowed immediately, building a fab takes 3 to 5 years. Qualifying it for automotive and defense supply chains takes another 2 to 3. By the time a Western mature node fab reaches full production, China's capacity advantage will have widened further. The export controls that were designed to contain China's semiconductor ambitions addressed the ceiling the most advanced chips China could build. They did not address the floor, and it turns out the floor is what most of the world actually stands on. Step back for a moment and look at the pattern. Nvidia's stock price passed $3 trillion. TSMC became the most valuable company in Asia. The US, Europe, Japan, and South Korea poured over $200 billion collectively into semiconductor strategies. The advanced chip race consumed the attention of every policymaker, investor, and journalist covering technology. And while all of that was happening, China executed arguably the most consequential semiconductor strategy of the decade, not by breaking through the export controls at the top, but by building an industrial empire underneath them. There is an irony here worth stating plainly. The export controls that were designed to limit China's semiconductor capabilities may have accelerated this outcome. Before the restrictions, Chinese chip makers were investing across the full spectrum, including attempts at cutting-edge production that consumed enormous capital with limited success. The export bans made the cutting-edge path functionally impossible. That forced a reallocation. Capital, engineering talent, policy attention, and government subsidies that might have been spread across the entire semiconductor stack were concentrated into the one area where China faced no equipment restrictions, no technology barriers, and no meaningful competition from Western industrial policy. The restrictions did not stop China from becoming a semiconductor power. They channeled China into becoming a very specific kind of semiconductor power, one focused on the exact chips the West was not protecting. The chips that cost 40 cents, the ones in your car's airbag controller and your hospital's patient monitor, and the power converter in your building's HVAC system, the ones no one notices until they are gone. Those chips do not win technology awards. They do not appear on earnings calls. They do not make magazine covers. But they are the layer the modern world runs on. And the country now building that layer at scale is the same country that every Western semiconductor policy was designed to constrain. The export ban said, you cannot build the most advanced chips. China's answer, apparently, was, we will build everything else. And right now, it is not clear that anyone has a plan for what happens when they succeed. Subscribe. The next video covers a dependency that runs underneath this one, and it is one most governments have not even started to address. Look around you right now. Name one machine in your house or car that you are now not sure who made the chips inside. Drop it in the comments. I want to see the list.